Okay, so we closed the last segment of this lecture saying that the semiconductors have a conductivity behavior in which the conductivity increases with temperature, but they can actually have two different regimes. One in which the conductivity is intrinsic, so just the band gap jumping as a function of temperature. But they can also have an extrinsic regime of semiconductivity in which you have some extra mobile carriers over here they just insert into the structure. Now, to start off with the intrinsic, because they do deserve some attention, they are often in this type of arrangement, which is the same arrangement that we were discussing before with diamond. So, technically speaking, the same business as diamond. But usually it's materials like silicon or germanium, the original thing. They're usually group 4 element. As pure materials in their own right, the band structure is set in exactly the right way for you to have that band gap jumping as a function of temperature. But as you go down in the group, you can see that the band gap energy change even though you are in the same group. So carbon in its diamond form will have a band gap of way more than 4, like 5.5 electron volt, impossible to jump with just thermal energy. When you go down to silicon or germanium, this thing decreases of like a factor of 5, so you go to 1.1 electron volt or 0.7 electron volt. So this is easy to jump with just thermal energy. And as you go down in a group, that's the point where the periodic table has the transition between metal and semi-metal, and you end up in tin, and tin as a material has a 0 electron volt band gap. It's a metal. There you don't have to jump anything, it will conduct electricity as it is. Why does this thing happen? Because of the intrinsic characteristics of the bonding and of the orbitals involved in the solid, because when you are up here, so the first row, second, third row, you actually change the energies of the orbitals involved in the valence shell bonding. So the splitting that you end up having changes, and the splitting between the bond between carbon and carbon is completely different from the splitting between the bands of the molecular orbital of silicon and silicon. So the more you go down, the more you reduce the split that you have between the bands. You still have the bands because you're still in a solid, so you still have to consider the interaction among all atoms involved in this whole business. Now, when you have this band gap, so band of the valence, conduction band is completely empty above, band gap in between, the number of electrons that you find here, so above the band gap, these are the only electrons that can actually conduct. This is a function of the temperature and a function of how big is this gap. So if this gap is huge, doesn't matter how much temperature you put, the number of the carriers that you can actually drag up there will be abysmally low. If this band gap is smaller, for the same temperature, you end up with a lot more electrons up there. So in the way we treat band gap and band conduction, you have the negative charges, which are electrons in the conduction band, and the positive hold, so the thing that you leave behind on the nature of not having an electron in the energy state. So this thing is conceptually, like a positive hole is conceptually the absence of an electron. Why is it absent? Because it went up, right? So usually in an intrinsic semiconductor, the number of these two is equal, because anything that you leave behind, you left it behind because it's up here in the higher energy state. So if you apply a potential to your material, you will have the electrons moving towards the positive and the hole moving on the other side. And that's the reason why your material will conduct electricity, because you can actually put a circuit going on. But that's the intrinsic behavior. If you put an impurity in your material, then you can actually increase the conductivity. Now, the idea is that if you put silicon, so a group 4, with something from either group 3 or group 5, you make an extrinsic semiconductor. So if you add 0.02% of gallium to your silicon, then statistically speaking, there will be one bond in the whole structure, but not fixed, that is deficient of one electron. So there is a hole hanging around. So somewhere in this whole band arrangement is missing a hole, right? But the trick here is that we were discussing before that the band arises because you have a lot of atoms interacting with each other. If you don't have enough atoms interacting with each other, you cannot make a band, right? Because the band only comes because you have this interacting with 10 to the 10, 10 to the 20, 10 to the 50, 10 to the 75 atoms interacting with each other in the same arrangement. So with low gallium concentration, as will be this one, statistically speaking, you do have some gallium atoms hanging around in a material that is supposed to be only silicon, so the silicon is still making the band, but your gallium just has orbitals hanging around. It's contributing orbitals to this whole business, but they cannot make a gap. They are empty discrete levels just above the valence band of your silicon. Why just above? Because it's a group 3 element. They need to be above in energy. This means that the gap here is super tiny. Like it's almost non-existent. Instead, you're here with 1.1 electron volt. This is an order of magnitude lower. So any energy, any vibration will just pop one of the electrons from the valence band into what are called the acceptor levels. By nature of popping these electrons in a discrete, localized, not band level, the electrons cannot move anymore. They are in that nice energy state, but they cannot go around because there is nothing neighboring in which they can actually stay in the same energy and do this whole business, and the gap up here is still pretty big. But the thing that they leave behind is the actual holes. So the absence of electrons down here makes this thing hole conductive. So the absence of an electron actually makes positive holes left behind in the valence band that can conduct electricity. Conceptually speaking, a hole does not exist. So by itself, it doesn't conduct electricity, but in solid state, we call a hope the absence of an electron, meaning that if you move a hole in one direction, it's because the electrons are hopping into the hole and moving in the other one, right? But it's an easy way to conceptualize it mentally, because then you can just think of, oh, you will have this type of behavior with this potential, but it's still just the electrons conduct electricity, yeah? Then your other option, after this positive hole or p-type semiconductor, is to go the other way. So if you use a group 5 element like arsenic, still super tiny amount, but statistically speaking, there is something in this whole business that is not silicon. But this time, your dopant is a group 5, so the energy is completely different of these donor levels, which are localized, because there is not enough arsenic to make a whole band, but the orbitals concerned with this whole business are just below the conduction band of the silicon. These are filled because arsenic in group 5 has more electrons than the silicon would have being group 4. So you can jump up very easily because this is a super tiny gap, and at that point there are extra electrons in the conduction bands that have nothing to do with the temperature. So here you jump from the localized level into something that is a band. So when you are in a band, then you can easily conduct because you have mobility in an energy space. Yeah? So the donor level effect is increasing the carriers in the conduction band and makes the material able to conduct even when the energy is too low for electrons to go from the valence to the conduction band. This is what we called an N-type semiconductor. Why N? Because the electron is negatively charged. Yeah. Extrinsic semiconductors are the concept that will be very much recurring in solid-state chemistry, which is you can put defects in your material. So if your material is a nice lattice of a lot of atoms all arranged periodically in space, statistically speaking, you can just change something and keep the same lattice, but drag something out, put something else in, change the properties. This thing is possible because it's a whole solid. You cannot do this in a single molecule. If you change an atom, you disrupt the molecule. This is a solid. You have 10 to the 120 atoms. If you change a fraction of them, so 10 to the 2, who cares? You can still arrange them, right? But they can add that tiny little spark into your material that makes it do something different. This concept will be explored more in PBL, and it's the thing that makes this thing called like a dopant in your material. So you have an additional spark that makes the material work. So if you imagine that this is your solution, this is a solute. If they are small enough in concentrations, you can make the rest of the arrangement hold. For a dopant to be able to do the thing that you want it to do, you need to check how big it is. What is the oxidation state in comparison to all the rest of the atoms? What is the geometry that it likes to have? So what is the coordination that it would like to acquire? Because if it's exactly the same as the coordination that you have available in your material, then it's Gucci. But if it doesn't like the coordination, it might actually try to rearrange itself in a very different way. Sometimes good, sometimes bad. Often you do need a bit of luck. So you might have an idea of something that you want to put in your material. Your material might tell you absolutely not, or it could be perfectly happy with it. So it's a mixture of skills and sometimes just getting a tiny bit lucky. Usually when you change the composition of a material, especially when you change it off a lot, you call it making a solid solution. So you have solid A, solid B, and solid AB, that is a mixture of the two in between. Now, this type of trick is also something that we want to consider when we go into another type of business, because we saw basically main group semiconductors that are sort of the standard of how you think about it. You have this nice band, you call the band, you put the dopants, you do the thing, all fine as long as you are in the right semi-metal range of the periodic table, and sort of easy to conceptualize. But then when you go into other type of material, because no one forces you to have a single atom material and call it a day, every material will have to have a bond description with molecular orbitals, and in its own right will have electrons. So what is going on, right? So if you do stuff with, for instance, manganese oxide, iron oxide, cobalt oxide, right? Theoretically speaking, band theory should satisfactorily account for everything that you have going on here, right? But when you go out, because these are transition metals, manganese, iron, cobalt, D5, D6 outer shell, the business becomes a bit more complicated. So you still keep this type of structure, like the rock salt, which is the same structure as sodium chloride, but with different components inside. So technically speaking, when you start to involve d orbitals, as you have 1s, 3p, 5d, if you start to have a d5, as we were saying, then if we were to stay in the same mindful arrangement as we were before, you overlap all of this. They are half-filled, so if you have 5 of this, 5 bonding, 5 anti-bonding, if you have enough of them, you make a whole band, the band is half full, your material is a metal. True? No, these materials are semiconductors. And when you actually do the computed bond structure by making the molecular orbitals, these are real ones, not the box one that we have, you can actually see that there is a gap between the states. So it's not contiguous, you don't have all of them, you have a gap in between. So they can be semiconductors, you can jump this gap, but they're not metallic. Note, first of all, that here we were putting them all at the same energy arrangement, so the generate orbitals all at the same energy, as you would expect all the p orbitals to be at the same energy. But for transition metals, you start to have additional complexities. So the first thing that you do is you have a coordination of atoms around it. So you have your manganese, all the oxygens around it. This already shifts the energy. So for those of you who followed inorganic chemistry, this is the splitting. For those of you who did not follow inorganic chemistry, this is the splitting. So by nature of having a coordination, the 5 d orbitals that you had hanging around will not have the same energy anymore, because some will feel the presence of the oxygen around it differently, and you will already find yourself with 2 different energy levels. So when you go and do a band, the band might leave a space behind. The orbital overlap might or might not happen on the basis of what? Let's go to another example, because titanium oxide and vanadium oxide have this exact same business. So then you have a D2 and D3, because they're not D5, D6, they're in a different point in the transitional metal groups. So you can have 2 here, 3 here. Same business as before will mean that these are semiconducting, because the one before were semiconducting. No, these ones are metallic. So this one actually have the half-filled band. The one before did not have the half-full band, they had a gap in between. Super annoying. Why? Because as you progress in the series, you have a different business with these orbitals being involved with each other. Because as we were saying before, you can only have band behavior, complete, full, perfect band behavior, if your orbitals are smoothly interacting with each other and you can consider them to be delocalized through the structure. So the molecular orbitals are all nice and spread. Now, when you have the early transition metals, this thing can actually happen. So stuff like titanium, vanadium, they're over here, so closer that side. Then you can actually consider them interacting. The more you go on the other side, the more you increase the electron counts. So the shielding of your nuclei and the amount of atoms actually changes. And the more charges do you put on your atom, the more the orbitals, especially orbitals like the d orbitals, will start to shrink and actually stay closer to the atoms, which make d orbitals, and even more so f orbitals of the lanthanides, having a tendency to localization. So you are on the atom. You can see that since you shrink here, this same business could be nice and bandy, or you will have gaps because they don't interact with each other. So you have a lot of them, you still don't have a single atom, but they're sort of like in narrow distribution, and you might have jumps between them. So the more you go, depending in the transition metal series, the more this business of the band needs to be slightly reconsidered. So if the orbitals are more tightly held, you have something that is localized instead of having this band that encompasses the whole business. Yeah. So this motion still, because you can jump between vaguely localized orbitals, still temperature. Temperature is always the thing that allows you to make a trick. So the semiconductor in which you don't have the possibility to apply band theory as smoothly as we did before, but still behave in a way that we can rationalize with semiconductivity and the band movement, are called hopping semiconductors. So you need to jump through different levels. The levels are sort of localized instead of being a nice smooth band, but then you can jump from one to the other with the activation of thermal energy. The more you do tricks with these bands and you do tricks with the transition metals that are involved, the more you can actually rearrange the conductivity. So the conductivity in transition metal compounds increases when the transition metal that is involved in this whole business has different oxidation states. Why? Because then you have the same orbital arrangement, different electronic occupation. Example of this, so we don't go absolutely crazy, nickel oxide. Now in nickel oxide you have basically this structure that you see over here, same rock salt arrangement that we were discussing before. So you have nickel in the center over here, and then every nickel is surrounded by 8 oxygens, fine energy, okay, it's an octahedron, which means that the d orbitals involved in this whole business will not be degenerate. They are not all 5 at the same energy. You will start to split them in 2 different groups, 3 at the bottom, 2 at the top. When you have nickel oxide in nickel 2 plus, given the oxidation state and the electronic structure, then you end up having this D8 arrangement. So if you count 2, 6, 2, 4, 6, 8, so that's your D8 thing. This is green and insulating. Why is it green? Because you can also use the energy of photons to jump the gap, which is something that we're going to discuss in the next lecture. So you look at it, it's green, but in itself is insulating. So in itself it does not conduct electricity. You cannot bridge whatever gap do you have between here and being able to move between the states. When you increase the temperature and you are in air, the issue that goes on here is not that the band structure in itself really much changes or you give it so much energy that you jump the gap like it was nothing, but you can change the oxidation state of your nickel. So the nickel can be stable in itself, which is something that you never see in main group or alkali metals, in multiple oxidation states. So you could have a 2 plus or a 3 plus, but if you have a 3 plus, then you have this thing. So you have a space in which there are no electrons. Why? Because you oxidize the material in air. And this thing makes so that, statistically speaking, if you have some of these positions in which one of the orbitals is empty, then energy-wise, these see each other very well, and you can jump this into this, and this into this, and this into this, and the material goes from green to black, and goes from insulating to semiconducting. Nice. So the empty level that you have here can be thought as a positive hole, so nickel oxide is regarded as a p-type semiconductor. Note one problem, that this whole business, so how much do you conduct with nickel oxide, is very much temperature and oxidation state dependent. It's difficult to control. You do not want to do this type of game, because then depending on the atmosphere, depending on how high is the temperature, then your thing conducts in whichever way it wants. If you come back, it might not go back exactly as it was before. This is a level of variability that you do not want to impose to yourself, because it means that your material will have a behavior and you cannot control it. This is not something that we like in solid state chemistry. So we much prefer, using the trick that we were discussing before, doping the material. So if you mix your nickel oxide with lithium oxide under oxygen atmosphere, then it's the lithium in this whole business that induces the exchange. So having lithium inside makes so that you will have a mix of nickel 2+ and nickel 3+ as you did before. But this time, the concentration of nickel 3+ is directly and immediately and precisely correlated with the concentration of lithium that you put in. So when you are at level of lithium in your structure 0, then your structure is nickel oxide and has almost no conductivity, so 10 to the minus 10, this is an insulator. If you add as little as 10% of lithium in this whole business and you make a material that is almost a nickel oxide, but not quite, then your thing increases of like an order of magnitude or more, which is nice. And this is called controlled valency semiconductor. So you control how much is your material capable of conducting by deciding how much holes do you put in your structure. This is, of course, following the effect of the temperature. So this change in conductivity is at 25 degree, but it's huge. It's enormous for being something at 25 degrees. So you're a low temperature, speaking of general terms, and the jump in conductivity is impressive. These type of things, so controlled vacancy semiconductors and hop-in semiconductors, are used in every time you need to have a material that changes the conductivity as a function of temperature. So, and if it changes the conductivity, it also changes the resistance as a function of temperature. So these are things that you can use in electronics to control how much flow of electrons do you have, or how much resistance to the flow of the electron do you have. So you call this thermistors, and they look a bit like this. So when you have negative temperature coefficient, which is this thing, the resistance drops when you increase the temperature. So the more you increase the temperature, the better your material conducts. Sometimes you have the other way around, which is the positive temperature coefficient. The resistance increases when you increase the temperature. That's a completely different trick from the one that we discussed, but it makes so that your material is happy to conduct at lower temperatures. If you increase the temperature after a certain limit, it just becomes an insulator and you call it a day. You do not conduct electricity anymore. When you have your nickel with 10% or 5% doping of lithium, you have so the trick here is that if you are in the right range, so both here and here, your conductivity is linear with the temperature over a contained range, but this can be calibrated. So if you're in the right range, then you can be like, okay, my machine is calibrated, and I know that for every temperature that I read, this is the conductivity, or any flow of electrons that I read, this is the temperature, which is particularly useful. Our nickel oxide with 5-10% doping of lithium is a negative temperature coefficient material, and basically the conductivity that you have, so this type of process, follows the Arrhenius law. So depending on an activation energy, this is the function of the temperature, and if you stay below 200 degree, this can be linearized. So whatever you see, whatever reading you see, it can be calibrated against a mathematical law. So this is very nice and very reproducible and exactly what you want. This type of behavior doesn't happen in materials like this. You need to look into a completely different type of oxides like the barium titanate. The reason this shifts is because you have a complete rearrangement of the atoms in the structure, so the band structure goes completely to a different level. So depending on when you arrange the atoms, if the atoms move, because of reasons. The band structure splits and changes and breaks, and you cannot conduct electricity anymore. This is only one example that is relevant for what we were doing of applications of semiconductors, but semiconductors in general are one of the most applicable materials that ever walked the earth, and the only reason we're having this conversation over a video. And the applications of semiconductors in transistors, silicon chips and photocells is the basis of microelectronics, and we will discuss it in the lecture about junctions and photovoltaics. Now, this is the summary of your learning objectives for week 1. So when you look back into this lecture, you should be able to answer these questions with confidence. And with this, we conclude the lectures for the week. I would encourage you to leave any doubts or any big question marks or stuff that really escaped you in the feedback fluid document, and also reply to other people that might leave it. And we will see each other on Tuesday for the Q&A. See you soon!